Hello, everyone, and welcome back. In today's lesson, we're going to talk about a couple of different sets that are associated with a linear transformation called the domain, the codomain, the kernel, and the range of a linear transformation. Now, domain and range mean the same things for a general transformation T that they have meant for algebraic functions throughout all of algebra. When we talk about domain and range, the domain of a function is the set of all the valid inputs for the function. And range captures everything that T can produce, everything that can come out of the function T, all possible outputs for T. So domain and range mean the same things that they always have, all possible inputs and all possible outputs. Now, the word codomain is something that would be new for us at this point. When you're talking about a general function t, the codomain is telling you the type of outputs that t is producing. So the codomain tells you whether your function is producing real numbers, is your t producing algebraic functions, is your t producing two-dimensional vectors, is your t producing three-dimensional vectors. The codomain tells you the type of outputs being produced by your transformation t. Now, some notation. If you see the notation t colon S1 arrow S2. This notation tells you that the domain of T is the set S1 and the codomain of this T is the set S2. So for example, supposing that we have a linear transformation T, and T takes in two-dimensional vectors as inputs, and if it produces real numbers as outputs, the way that we would write that in symbolic notation is that T would take inputs from R2, the set of two-dimensional vectors, and it would produce outputs in R, the set of real numbers. So R2 would be the domain of this transformation. Two-dimensional vectors are going into the function, and R would be the codomain of this function because these are the types of the objects that this particular function is producing. So if you've ever done any programming where you've had to create your own function or method in the code, you'll be familiar with this idea of domain and codomain already. Because when you create a function or a method in code, most programming languages either encourage or require you to tell the computer what kind of objects are going into the function and what kind of objects are coming out of this function and are being produced. So, for example, right now I'm mostly using the programming language GDScript. And in GDScript, the kind of setup that you would need to write when creating a function is some syntax like this: func for func for function. Then the name of the function, for example, here, this function is called myTransform. Then you have the name of your input. I've just generically called it input. And then right here, I'm telling the computer the type of the input. These inputs going into this particular function are of type vector2, so you should expect coming into this function a vector with two entries. Here next to the arrow, I'm also telling the computer the type of the outputs. I'm saying, and here's that right arrow that we saw above. Here is the type of the outputs. The outputs are of type vector3. So in the language of this class, this particular method and function that I've defined in code would have a domain R2 because vectors of 2 entries are going into the function, and it would have codomain R3 because 3-dimensional vectors are coming out of this function. So this concept of domain and codomain is very familiar to those of you who have created methods in code. So let's go ahead and practice finding the domain, the codomain, and the range for a certain given linear transformation. For example, let's have t be the function which takes 2-dimensional vectors and does a projection. And it projects those vectors onto this guy here, w equals 1, 3. So the first question is, what is the domain of this linear transformation? What kind of stuff is going into this function and is being acted upon? Well, that much is given to us directly in the problem statement. The job of t is to take 2-dimensional vectors and project them onto this guy w. So if the function is taking 2-dimensional vectors, the domain of t would be the set of all 2-dimensional vectors called R2. So then it's a question of what is the codomain of t? What is the type? What is the format? What is the nature of the stuff that t produces? So the question really is, what kind of objects can you expect to result when you project a vector onto another vector? And we remember from our lessons on projection that projection onto a 2D vector produces a 2D vector. So the codomain of this function, the type of outputs it produces vectors of type R2. So now by contrast, let's talk about what is the range of T. We've talked about that the type of the objects it can produce are objects of type 2-dimensional vectors, but now the question is, okay, actually which vectors in R2 is T capable of creating? So let's think about that. We have our vector W here, and we're projecting onto the vector W. And we remember from our lesson on projection that when you project a vector onto W, you get another vector that lies somewhere along this line spanned by W. So I'll note that the projection is always a scalar multiple of W. So the actual vectors that T can produce are vectors of the form some number times W. Some vector of the form C times 1 in the first entry and C times 3 in the second entry. Some scalar multiple of W. Those are the actual 2-dimensional vectors that T is capable of producing. Let's do another example. Let's let T be the function that takes in a 2-dimensional vector and performs the action of dotting that vector with W. Once again, W is the vector 1, 3 from last time. So once again, what's the domain of T? Again, the domain of T are going to be the 2-dimensional vectors because those are the vectors that I'm giving to T that I'm asking it to then dot with W. But now I'm asking, what's the codomain of T? What are the types of items that are produced when you calculate a dot product with a given vector? Well, when you dot two vectors together, the result of the dot product is always a real scalar number. So because the outputs of this action are always real scalar numbers, we would say that the codomain is just R, the set of real scalars. Now for the range of t. And so the question is there any limitation or restrictions on the actual set of real numbers that t is capable of producing? And in this case, no, there are no restrictions on the real values that t is actually capable of producing. For example, if I apply the transformation t to any vector of the form c comma 0, t's job would be to dot that c comma 0 with the vector w being 1 comma 3. And the result of that vector would be equal to whatever real number you placed here in the x component of your input. So no matter what output that you wanted to get, you can achieve that output by just putting that value in the x component of the input. So it's possible to achieve any output, any real number out of this transformation, and as a result, the range of t is the entire set of real numbers R. Let's again practice with a linear transformation t. And t's job is to left multiply, and I'll specify left multiplies vectors by the matrix given here. A matrix with 3 rows and 2 columns, 1, 0, 0, 0, 0, 0. So the question is, what is the domain of this t? What kind of stuff can be multiplied by the matrix A like this one? So if I think about applying t to an input vector, if I think about left multiplying that vector by A, because the matrix A has 3 rows and 2 columns, V would also have to have 2 entries in order for that product to be well defined. Those two values in the middle, 2 and 2, would have to match. So because the vector v has to have 2 entries in order for this product to be defined, the domain of t, the kind of stuff that t can take into itself, the inputs are of type R2, vectors with 2 entries. So now let's think about the codomain of t. What kind of stuff does this transformation produce? Well, if I take a 3 by 2 matrix and I multiply it by a 2 by 1 vector, we remember from our lesson on matrix multiplication that these two inner dimensions basically cancel out and give you a result that is 3 by 1 in the end. In other words, a vector with 3 entries. In other words, a vector in R3. So the type of vectors being produced by this action are vectors that have, in the end, 3 entries. So that's our codomain in this case. Now someone says, okay, your outputs are of type R3, but what's the actual range of your transformation? What's the actual set of vectors that this transformation is capable of producing? So let's think about that. Let's think about what kind of results you can get if you take a 2-dimensional vector and multiply it by this matrix. I'll go ahead and set up just a generic arbitrary 2-dimensional input. I'll call it x comma y. And I'll think about what happens if I multiply that vector xy on the left by this matrix. If I use the techniques of matrix multiplication to get this result, I'm ending up with, in the first entry, x from 1 times x plus 0 times y. And then the dot products for the last 2 rows just vanish and become 0. So the outputs of this t, the actual vectors that t is producing, are only the vectors that lie along this particular line in 3D space. The vectors that are scalar multiples of 1, 0, 0, vectors that lie along the x-axis in 3D space. The range of T is the vectors of form some number 0 and 0. In other words, vectors that lie along the x-axis in 3D space. T is not capable of producing just any three-dimensional vector. This particular T is quite limited in the vectors that it can produce. It can only produce vectors that have some value in the x component and zeros in the y and z component. Now let's talk about the kernel of a linear transformation. When we're talking about kernel, first of all, let's note that when you're dealing with the domain and the codomain of any linear transformation, those domains and codomains have some element inside of them that serves the role of zero. And the appearance and the shape of that zero can be different depending on what codomain you're in. So for example, if you're working with a function that has a codomain R, just the real scalar numbers, then 0 within that set would just be the real number 0. If your codomain is R2, then 0 would be the vector that has 0 in these two entries. R3 would have a vector that has 0 in all three of its entries. And similarly for Rn, if you're dealing with a set of algebraic functions, then 0 in that context is the zero function, a constant function that outputs 0 at all times. And matrices, if that's your codomain, that has the zero matrix, which has 0 in every entry. So the zero element can look a little bit different, but they have this sort of common thread that it's zeros in every relevant position. When we talk about the kernel of a linear transformation, this word kernel means all of the inputs that become 0, whatever is the zero element of the codomain, all the elements that become 0 after t is applied. The kernel is the set of all inputs that become 0 after t is applied. The kernel is all of the stuff that turns into 0 after being transformed by the function. So for example, suppose that I'm dealing with the linear transformation t, whose action is to take derivatives of functions. And someone says, describe the kernel of t. So essentially, what I'm asking is, if I apply t to a certain input, in this case a real function, what causes 0 to result from that? If I take the derivative of a certain function, what causes 0 to result from that? Well, if you take the derivative of something and the derivative becomes 0, that only happens in one situation. This happens when you're taking the derivative of a constant function. When you take the derivative of a constant function, the result of that action is always equal to the 0 function. So what we would say in the new language is that the kernel of this transformation is the collection of all the constant functions. The kernel of t are the constant functions because those are the guys who become 0 after the transformation is applied. Let's do another exercise. Let's consider the transformation, which takes two-dimensional vectors and projects them onto this vector w equals 1, comma 3. We've already described the domain, the codomain, and the range of this function. So now let's go ahead and describe the kernel of this function. And let's think about everything that becomes 0 after this transformation is applied. There are two ways to think about this situation to answer this question. I would say the first one is to reason using the projection formula. And the second way is to reason using graphical reasoning. Now, if you use the projection formula, and I imagine taking the dot product of v with w divided by the dot product of w with itself, and using that scalar multiple and applying it to w, under what circumstances am I going to get the 0 vector as a result of that action? Well, imagine, we have this vector w, and we're scaling it by some number, and we're getting 0, 0 as the result. The only way that this is possible is if the actual scalar c is the number 0 itself. If c is equal to 0, then that will turn this 1, 3 into 0, 0, that vector. Now, because in projection, the scaling formula is given by these dot products, v dot w over w dot w, what we're basically saying is that if your projection is resulting in the 0 vector, then v dot w divided by w dot w has to be equal to 0, the number. And the only way for a fraction like this to become 0 is if the quantity at the top of the expression is equal to 0. So really what's going on here is that if v dot w is equal to 0, then the projection is going to result in the 0 vector. Now, when two vectors have a dot product of 0, that implies that v and w are perpendicular. So under what circumstances are you getting the 0 vector from this projection? You are getting them when you are projecting a vector v, which is already completely perpendicular to the guy that you're projecting onto. So this would be one way to reason that the kernel of this transformation t, the set of all vectors that become 0 after the action of t is applied, the kernel of this t is going to be all vectors perpendicular to w equals 1, 3. If you have a vector that's perpendicular to this w, and then you project it onto w, then you're going to get the 0 vector as a result. So vectors perpendicular to w form the kernel. Now to see this situation graphically, let me suppose that I am projecting onto the vector 1, 3.
Note from editor Sam. I accidentally drew the onto vector as 3, 1 instead of 1, 3.
And so from this image, I can see that if I position u so that it is at a perfect right angle to v, so that u and v are perpendicular, then the shadow cast by u onto this line spanned by v shrinks away and becomes ultimately nothing. Perpendicular vectors become 0 after the projection is applied. So perpendicular vectors are going to be in this transformation's kernel. So let's go back to this transformation whose job is to take vectors and multiply them on the left by this matrix A, 1, 0, 0, 0, and 0, 0. So let's now describe what is the kernel of this particular transformation. What kind of vectors become 0 after this transformation is applied? So let's imagine taking a generic vector v. I'll just call its entries v1 and v2 for the moment, multiplying it by this matrix A and thinking about what is it going to take to get 0 as the result. In this case, if I go through on the left and complete that matrix multiplication, if I do that matrix multiplication on the left using the standard dot product technique, then on the left I get v1, 0, and 0 from that calculation. And I want that result to be equal to the vector that has 0 in every single entry. Well, what I can see is that the vector on the left is going to be equal to the vector on the right if that v1 entry is equal to 0. So what I would then say is that the kernel of this transformation is going to be all the vectors of the form 0 as your first entry, and then whatever as your second entry. As long as that first entry is 0, then after applying the transformation, after multiplying by this matrix A, the result will be equal to the 0 vector in the codomain. Now, one thing worth noting that if you're dealing with a linear transformation, the kernel is always going to have at least one element inside of it, and that is the 0 that's in the domain. So to explain why the 0 element of the domain always becomes the 0 element of the codomain, let's think about applying the linear transformation t to the 0 of the domain. So I'll go ahead and call the 0 element of the domain something like z subscript d. That's whatever the 0 is in the domain of your function. So let's imagine plugging that value into our linear transformation. Well, if you take the 0 element of your domain and you scale it by another copy of 0, when you multiply 0 by another copy of 0, nothing changes, right? So now I'm going to use linearity of t to take that 0 and factor it to the outside. I'm using that property of linear transformations that says you can change the order of operations without changing the result. You can multiply the inputs by 0 and then apply t to the answer. Or you can apply t first and then multiply by 0. So I have used that linearity property. I've used that constant multiple rule to pull this scalar 0 to the outside. Well, when you multiply anything by 0, it becomes 0. Specifically, when we multiply by 0, we get whatever is the 0 element in our codomain, which I will call z sub c for short. So all this to say that if you apply a linear transformation to 0, you get 0 as a result. And therefore, the 0 of the domain is always in the kernel of t, because the kernel is all the stuff that becomes 0 after the transformation is applied. So the 0 element is always in the kernel. 0 is in the kernel no matter what if you're dealing with a linear transformation. It's just that some transformations may have other stuff in the kernel besides 0. Finally, let me just speak a little bit about what kernel is saying to us about a transformation. So when we talk about kernel, you should understand the kernel as conveying the information that is lost or destroyed or collapsed as a result of applying a linear transformation. So for an example, let's imagine that we are performing the action of taking a photograph. You have some three-dimensional world, and you take a photograph of that world, and that turns the three-dimensional world into a two-dimensional picture. When you do this action of taking a three-dimensional world and pressing it onto a two-dimensional picture, a lot of information is lost, right? You're losing, for example, depth information. So if I wanted to describe the kernel of this action of taking a photograph, the kernel of this action would be all the depth information that the photograph is losing, compressing, destroying. All of the depth information that that transformation cannot retain or capture. So in summary, when we think about a linear transformation T, there are four different sets at play. There's the domain of the transformation T, and that tells you the type of inputs, the type of objects that are going into your transformation. Then you have the codomain, which is telling you the type of your outputs, the type of objects that are being produced by your transformation. You have the range of T, and that tells you everything that your transformation can actually produce and generate, all of the possible outputs of your transformation. And notice that the range is a subset of the codomain. The range is a subset of the codomain representing all the outputs that T can actually produce. Meanwhile, the kernel is a subset of the domain. The kernel represents essentially everything that the transformation destroys and turns into 0 after the transformation is applied.